Okay.
For just a moment, but they'll come back.
All right. Oh. Okay, we'll go on and get started. So thanks everyone for coming this morning. My name is Bennett. I'm a program manager on the Direct3D team, and I'm here today to talk about DirectX performance and your game. When we've talked about DirectX 12 performance, we always say it's low level, it's efficient. And the goal of this talk is to talk about the features and APIs within DirectX 12 that can let you exploit the GPU in new, more efficient ways and to get better performance in your game. So the general structure for the talk is we're going to give a quick overview of what DirectX is, where we've been, and then we're going to dive right into the APIs and the specific features. So we're first going to talk about GPU efficiency. What features are in DirectX 12 to enable your game to be more efficient on the GPU? Really key if you want to run at higher resolutions, render more rich content. We'll then go into reducing CPU overhead, making sure that your game is never CPU bound with DirectX 12 and letting you get the most out of thermally constrained systems where the CPU and the GPU have a shared thermal budget. Finally, we'll do a summary and next steps, and we should have time for Q&A after. OK, so what is DirectX 12? We've designed DirectX 12 to be a single API that provides low-level access to a variety of GPU hardware. It's a much lower abstraction than DirectX 11, but it works equally great across a number of GPUs. We worked very closely with hardware vendors to achieve that. And the whole thing we're going to come back to in this presentation is that it's not just about being lower level and working with the hardware more directly. The real value here is that it enables your game to exploit the higher level knowledge it has about when resources are needed, how they're going to be used, what order you're going to be doing rendering operations in. And by giving that information to the driver and to the hardware, you can get awesome performance gains on the CPU and the GPU. So today we're going to discuss specific best practices around particular DirectX 12 APIs so you can see what's possible with the API. So let's jump into GPU efficiency. There are three key areas that we're going to cover today for GPU efficiency on DirectX 12. The first is manual resource usage management. We'll talk about what it means to explicitly transition resources between different states and what opportunities that provides your app. We'll then go into parallel GPU execution. Modern GPUs have the ability to perform multiple tasks in parallel, and we'll talk about why that can be a really powerful use case for your game. And finally, we'll talk about GPU-generated workloads, having the GPU generate instructions for itself, and the efficiency that enables, and the new approaches to rendering that can enable around culling and things like that can really move the performance needle for your game. So for the first two of these, it's really about doing existing things more efficiently, using the new APIs to perform tasks in a more efficient manner. And then the third area is really a new way where you can take new rendering approaches with Direct3D 12. OK, so explicit resource transitions. What is a resource transition? Why do we need it? Modern GPUs require resources to be in different states, depending on how the pipeline is going to use it. Modern GPUs are, of course, incredibly complex and have a very deep pipeline. And depending on where a resource is going to be used, they want it to be in a different state. The canonical example here is basically having a single texture as both a render target and as a texture that you're going to read from. Some GPUs, if it's going to be in the render target format, can have it actually compressed and actually save bandwidth as they're writing to that texture. But when they want to read from it, they have to decompress it. It has to be in a different hardware state for the other parts of the GPU to read from it efficiently. So we have different states for memory on the GPU. That's one thing. But also, when you're transitioning between different uses for a resource, you want to make sure that the synchronization is correct. GPUs want to make sure that all writes to a render target will be resolved before you begin to read from it in a subsequent step. So it needs to know when a texture is going to be in use. So in DirectX 12, the app is responsible for identifying when these transitions need to occur. In DirectX 11, the driver could kind of pick up hints from the different high-level APIs we had, like OM-set render targets, PS-set shader resources. In DirectX 12, the app will tell the GPU, I used to be using this resource as a render target. I'm now going to use it as a shader resource view. Do whatever hardware-specific transitions you need to do. And so this is needed for multi-threading, absolutely, but it enables some really cool perf optimizations in your app. So of course, making these transitions yourself, it tells you, the developer, when you're asking the GPU to do work. Some of these things they were already happening in DirectX 11, but they would happen in an abstracted way. With DirectX 12, you know when you're asking the GPU to move something from one state to another, and you can take care then to make sure you're ordering operations in a way that minimizes these transitions. And there's a whole bunch of different states in DirectX 12. Render target, shader resource view, copy source, copy dest, MSA resolve. There's a whole bunch of different ones. So it's up to your app to see what states are available and to minimize these transitions. So you're now more aware of what's happening on the GPU. There's less unexpected stalls and costs coming from there. But it also gives you a really cool opportunity to eliminate unnecessary and redundant resource barrier transitions. You can do this both in the app and in the driver by giving the driver more information about how you're going to be using a resource. So the first case we're going to talk about is UAV synchronization. This is a very cool way that you can get a lot more performance out of compute workloads with DirectX 12. So in DirectX 11, the general rule was when you would do multiple dispatches back to back, the API would guarantee that all writes and reads to a particular UAV would be complete on a particular dispatch before the next dispatch would occur. And this was a great safe rule for apps. It ensured correctness and predictability. And the way this would happen is in DirectX 11, the driver would insert these stalls after a dispatch call when you do these back-to-back to ensure the correctness of ordering, since these pipelines are so deep. So what this might look like is you have a dispatch, and then you have a wait for idle, a dispatch, and a wait for idle, and then another dispatch, and so on and so forth. With DirectX 12, now you are responsible for telling the driver when these waits are actually needed, or whether all these dispatches are writing to unrelated parts of a UAV and can be completely independent. So what the diagram might look like when you remove these wait for idles, if your app has a higher level of knowledge that they're not needed, is that these dispatches can run back to back without these costly idles. But even more than that, more than removing these idle commands, GPUs can actually run multiple dispatches in parallel. And this is really key if you have a large number of small dispatches. We've seen many algorithms that have a large number of dispatches with a single thread. GPUs can dispatch hundreds of compute threads at once. And if it's trying to wait between them, it can only run one at a time. So by removing these waits, you can actually run hundreds, or up to 100, dispatches at once and get a dramatic improvement in efficiency. So let's actually take a look at what this can look like. We've been working with, I'll switch to here. We've been working with Lionhead Studios to adopt DirectX 12 with Fable Legends. And they've done a fantastic job on it. And we have a version of the game here running live clearly. And what we have right now is the DirectX 11 behavior. Fable does a number of dispatches for culling operations in the game. You can see we have the frame rate up on the top right corner, top left corner. And we're getting good performance. It's about 50 frames a second. So what we've added the option for the purposes of demonstration is we've added the option to basically do the 11 behavior, which is what we're doing now, and then to rely on the app's higher level knowledge of when these stalls are actually needed, when these barriers are absolutely needed, and when they can be removed. So I'm going to toggle an option right now to use DX12 optimizations and to remove these barriers when they're unnecessary. And as you can see, we get a dramatic performance improvement just from this optimization, upwards of 20%. So this capability frees apps to use dispatches how you want to use them, and it can enable really awesome performance improvements that we're excited about. So that's UAV barriers. This is now under the app's control. The driver isn't making any assumptions for you. It's up to your app to have the higher level knowledge and use these only when they're appropriate. And if you want to use them after a dispatch, you'll just be like DX11. You're not going to get worse performance, but there's an opportunity here to improve. OK, there's a second case where resource barrier can provide more information to the driver and more information to the hardware than what was previously possible under DirectX 11. So as we said, when you want to use a resource for a different case, for a different usage, you have to call this API called resource barrier to tell the GPU, I was using it as a render target. I'm now going to use it as SRV, do the hardware transitions, insert the stalls, insert the synchronization, the cache flushes that your hardware needs to ensure correctness. What we're adding the ability to do with DirectX 12 is to perform these transitions over a period of time. It's a very common use case for you to have a render target that you then want to read at a later time, but you might not need to read it for 10 milliseconds or maybe until the next frame. So with DirectX 12, we give you the ability to perform these transitions over a long period of time or a short period of time by splitting a resource barrier call into two parts, the begin and the end. And both the begin and the end have the before and after states for the resource barrier. So the driver will see a beginning operation. It'll say, OK, we need to go to the SRV case. Normally, I need to do a wait. I need to do a stall at that point. But let's see if we're already going to do a wait or a stall and avoid this redundant operation. So a diagram that would show what this would look like before, if you're only calling a single resource bearer, is let's say we have a very basic rendering scenario where we're rendering to a render target. We then want to do the transition because we know we're going to need to read that in a subsequent shader. We then do some other operations. Let's say we do another API call that happens to be expensive, that happens to cause the GPU to need to idle. In this case, it's a set descriptor heap call. And then let's say we want to read from that texture. As you can see, during the course of this rendering, the GPU, the driver, generated 2 instructions and 2 commands to perform a wait. And these extra waits weren't really necessary because we're already doing a wait from the set descriptor heap call. But there's no way for the driver to know when you are actually going to read from that texture. It's very difficult to track and very expensive to track. So with this new API, with this new capability, you can tell the driver, I'm going to not use this resource for a long period of time. Don't be in a hurry to perform this transition. They can actually transition the hardware state lazily, and they can make sure that they avoid redundant idle commands and get a lot more efficiency from the GPU. So these are the 2 cases that can really get you a lot more performance from resource bearers and managing the resource state explicitly. It's, of course, necessary for multi-threading to work great in DirectX 12, but it also gives your app a lot more performance opportunities to take advantage of. The next section is parallel GPU execution. Modern GPUs have the ability to work on multiple tasks in parallel. If the app knows that I can do a 3D operation on one queue, one engine, while doing another simple task in parallel, and there's no direct dependencies between these, you can submit multiple workloads to the GPU and allow it to use its hardware in the most efficient manner. So the 3 different engine types that DirectX 12 exposes is 3D, which is basically what you might have thought of as a Direct3D 11 immediate context. It can do whatever operations you need it to. Hardware also has a compute engine, or compute engines, that can perform clear UAV calls, can perform dispatches, as well as copies. And finally, there's a copy queue, where you can perform basic copy operations. And you can use all these 3 queues in parallel if your app has that knowledge and has the ability to make use of, to predict which work you're going to be using ahead of time. So the first case we'll talk about is a copy engine. It's really great for getting data around without interrupting or blocking the main 3D engine. So for example, texture streaming, if you know that in 10 seconds from now you're going to need to access a new texture, or even if you know, hey, I want a new texture now, but it doesn't have to be immediate. I can wait a little bit. The copy engine allows your app to basically stream in copies from either system memory or within the main GPU without blocking the 3D engine. And this is really key, especially if you're going across the PCIe bus. The PCIe bus is relatively slow bandwidth-wise, and if you're doing a large copy from system memory, that copy can take time. You don't want to block the 3D queue and your rendering operations on waiting for this copy to lazily happen. So we have a quick demo of what this looks like. So we'll go in and close out of this. So we have a DirectX 12 conformance test that renders a Mandelbrot simulation while doing copy operations. And what you can see is the first time we run this through, we're doing the compute work and the copy work on the 3D queue. And you can see it renders moderately fast. The second iteration, you can see it's much faster. And that's because we're doing the copies, which don't need to interact with the compute work, on a separate queue. And as you can see with the numbers there at the bottom, we get a huge speed up. Near 100%. And just to visualize what this can actually look like, we have a copy of this app running under GPU view. GPU view is a tremendous tool available on Windows for visualizing what is actually happening on the GPU. And it's really of use for when you're trying to debug and understand how your work is submitting work to the GPU and specifically to multiple queues on the GPU. So in this case, this is the before, where you can see we have different packets of work going to the GPU. This packet of work contains the compute operation and the copy operation. And as you can see at the bottom here, it's about 92 milliseconds. So this is the first case that we're running at. So let's go over here to where we're using the copy engine at this point. And as you can see, the hardware is actually executing multiple command buffers in parallel. It's not serializing these behind your back. It's actually executing in parallel. And now if you look at the 3D work is only 41 milliseconds. And the copy work is only 27. So we've gotten a great performance efficiency improvement just by making use of these multiple engines. Okay, so that was about copy. We're really excited about compute as well. Compute is, of course, widely used in games today. It offers tremendous flexibility and power to come up with novel rendering solutions. And you can also take advantage of compute with DirectX 12 as well, running it asynchronously from the main 3D operations. So there's two notable use cases. Long-running, low-priority compute work. If you're doing a long simulation that maybe you don't need for 10 frames or even longer, you can run it at a low priority. The GPU will give whatever spare cycles it has to the compute work, and you can tell the GPU, I'll need it later. And at some point when you do need it, you can tell the 3D queue to wait on this actual work. So it's kind of great for long running, but it's also very good for using it with even in a single frame. Maybe you have a lot of work that's happening in serial, and there's a part of your frame that you can render on the 3D engine, and then you can go also to the compute engine. And maybe those both run for a handful of milliseconds, and then they merge back together. And it's up to your app to communicate the dependencies between all these different engines. So maybe you're going in serial, you go parallel, and each of them take about the same amount of time, but one's a little bit longer. If the compute engine is running a little bit longer, you can tell the 3D engine to wait on the compute work in a very efficient manner. This is on the order of microseconds. And the 3D engine work will proceed as quickly as it can. So how does this help? If you're just splitting the GPU in half and doing two things at once, does each task just take twice as long? Well, potentially, if you're doing the same type of work, but where you can really get gains is if you're doing different types of work on each queue. And the canonical example here is if you're doing a compute-heavy task, maybe on the compute queue, while you're doing a very bandwidth-intensive task on the 3D queue, where it only takes a few shader cores on the GPU to keep the bandwidth flowing for the main 3D operation, and that leaves the rest, the vast majority of the GPU, available for this compute work. So the classic case that we've encountered is you're rendering shadow maps on the 3D queue. You don't even have a pixel shader bound at all. It's very lightweight for the ALU, but there's a ton of bandwidth being used. In combination with a compute-heavy workload, such as lighting calculations or any other technique that you want to do. So we've seen great gains that are possible from this, and this is something that we think is possible in your game. And again, this is something that you can take advantage of using the higher level knowledge in your game. You can order operations intentionally to make sure that you can have a compute-heavy workload and a bandwidth-heavy workload operating at the same time. So this is something that your app can definitely take advantage of. So this is parallel GPU execution. And again, it's great for copy, great for compute, and it's something that you can take advantage of with the knowledge in your app. So let's go to GPU-generated workloads. We have introduced a lot of flexibility into the API, as well as a lot of new features that allow the GPU to be much more flexible about how it's performing rendering operations. You can take advantage of fixed function GPU hardware in whole new ways with DirectX 12. So the first case is queries. In DirectX 11, each query was individual. It was with the ID3D11 asynchronous class with the interface. And you could get the data on it whenever you wanted, and you could begin and end it whenever you wanted. With DirectX 12, we've changed the abstraction entirely, and we've introduced the ability for the app to group related queries together that are going to be used at similar time frames within a query heap. So you can create a query heap, maybe 10,000 queries up front, and you can execute individual queries within that heap, and then do a bulk resolve operation and copy that to GPU memory. So you perform a lot of queries, and then you do this one resolve operation, which says, hey, I want the data for that now. Store it in this GPU buffer. And the really cool thing about this is we've put the API signature here. It's just a buffer that you're storing the results into. It's total generic memory. It can be system memory if you want to access it on the CPU like you might today, but it can also be GPU memory if you want to consume the results of this operation within a compute shader. So the two performance opportunities here, beyond the flexibility and the new algorithms it enables, is that these batched operations are very efficient for GPUs to do. It doesn't have to worry about resolving individual query operations. But we've also introduced a new query type because of rendering scenarios that game developers have told us about, called binary occlusion. Today, occlusion queries will give you the number of hits on a particular query, and it can be 100 or it can be 1. But maybe all the app cared about was, is this object visible at all? It's either there or it's not there for the purposes of culling. So with binary occlusion, GPUs now have more information about your workload, and you can choose to take advantage of this if you're just only caring about whether an object is there or not. The GPU can, as soon as it sees a single hit, just early out and avoid doing any other processing. So this is a great way that you can tell the driver to be more efficient with the information that you actually want. We've also generalized predication. In DirectX 11, predication was tied to specific queries. We've generalized this to feed off of any specific buffer. So of course, you can use the results of a query. If you resolve to a buffer, you can then use that as input to the predication. But this can be any buffer. It's a buffer with an offset, and it can be a query result. It can be something you generate in a compute shader if you want to do that yourself, or it can be something you poke directly from the CPU with whatever bits you've set there. So we think that this is a great way to enable new rendering scenarios for your games and really improve the flexibility of predication so you can take advantage of this fixed function hardware that's available on all GPUs. So that was queries and predication. We've generalized this existing functionality, enable new areas of usage. The next area is something we're really excited about. We think that it's a great new way for apps to drive GPU workloads and enable new rendering scenarios. And we call that execute indirect. And essentially, it's an API for generating and executing GPU-generated workloads. On DirectX 12, we have broad hardware compatibility between this. On this API allows you to specify the number of draws and dispatches that you want to perform on the GPU, and to vary the parameters going into those draws and dispatches in really meaningful ways. We have vertex and index buffers you can change between draws or dispatches, but primarily draws. You can pass whatever arbitrary constant data you want to each draw, and you can actually change constant buffer, shader resource view, or unordered access view bindings per draw. So there's a lot of flexibility here, and it's available on all DirectX 12 hardware today. So this enables new rendering scenarios. If you want to perform culling operations on the GPU and then immediately consume that work instead of making a round trip to the CPU. But you can also get awesome efficiency improvements. So we have a quick demo here showing this running on an Intel machine. This is Windows' tremendous security improvements in work, making me wait. So what you'll see shortly. All right, awesome. OK, so we have a quick demo that Intel put together earlier this past year called Asteroids. And what Asteroids does is it stresses, of course, the GPU and the CPU to draw a large number of asteroids. So on DirectX 12, the way we implemented originally, you can see we get about 78 frames a second, which is really good. And if we pull up Task Manager, you can see the CPU usage is low. We're only running at about 40% GPU utilization. So we made two important changes to the app. We first want to stress execute indirect. And to do so, we changed the app to use bindless texture bindings. It's a very powerful technique for arbitrarily selecting which textures you want to use if you're going to be executing 1,000 draws back to back. So we made that change. A lot of keyboards, and they're all different. And as you can see, when we go to bindless, we get an improvement in GPU efficiency. We're rendering at a higher frame rate, and we dip our CPU usage just a little bit. So we're doing even better. But now if we go to execute indirect, that's the fourth mode, we get even higher GPU efficiency. We're not emulating anything in software. We're not causing the CPU or the GPU to do more work to support this flexibility. We're being more efficient, and we're rendering with dramatically less CPU usage. So this is an API that is very efficient, but is a lot more flexible than what you might have seen in the past. OK, so this API, as we've said, is always going to be efficient, but there's two ways that you can get even more out of it. The first is that we've added a max count parameter to the API. Your app might know I'm only going to be using up to 1,000 draws at any given time. And by telling the driver that, you can tell the driver to only allocate the memory or only perform the operations it needs to support that maximum arbitrary count. Along those lines, you can actually specify the count of operations on the CPU itself. Don't feel like you have to specify it or indirect it on the GPU. With DirectX 12, you can just pass it in right on the CPU. And the second efficiency improvement you can do is to group these execute indirects together and avoid, and to, if you can, generate the parameters for these calls in a similar area of time. The GPUs have to do extra processing to support this, so you can help them avoid redundant operations by basically creating the data for these calls in kind of a similar area of time, and then calling these APIs in a similar area of time. And if you can't do that, that's fine. You're going to be tremendously more efficient than you could be on DirectX 11, but this is a way that you can get even more performance out of the GPU. Okay, so that was the GPU efficiency section. We talked about explicit resource usage management, where you're telling the GPU how the app is going to use a resource at different periods of time, and the new flexibility and power that enables apps. We talked about parallel GPU execution, performing operations on different engines, and having the app have the knowledge to synchronize between these two engines. And we talked about the new flexibility and APIs that are provided with query generalization, with predication generalization, and this whole new execute indirect call that lets the GPU execute workloads that it generated itself without making a round trip to the CPU. So we'll now talk about CPU overhead. CPU overhead is, of course, very important for games. Depending on your system configuration, you might be CPU bound. You might want more CPU cycles for AI or other use cases. And this just makes sure that this enables apps to draw as many objects as they want without worrying about CPU overhead at all. You can keep the GPU totally occupied. So with DirectX 12, we like to say there's a lot of improvements just for showing up and using the API. We've worked really hard to optimize the runtime itself to reduce tracking and operations that you might not need. Notable changes going from DirectX 11 is there's no high-frequency ref counting anymore. When you bind a texture to the pipeline, we're not going to increment a ref count somewhere. We're not going to manage the lifetime for a resource. When you release a resource, it's immediately released, and it's up to the app to release it at the appropriate time. And this is much more efficient for apps to do than in the runtime. You avoid this ref counting overhead. There's no hazard tracking. If you bind something as a render target, we're not going to unbind it as an SRV. It's up for apps to appropriately manage that, and they can do it much more efficiently than the runtime certainly can. And finally, no state shadowing. If you want to retrieve what the currently bound viewport is, your app can track that yourself, and we're not going to impose this tax on all apps for all states that the app might not really be interested in. So there's kind of improvements we made in the runtime to be even more efficient, but there's also 3 big opportunities that apps can take advantage of to really move the needle performance-wise. And that's resource binding. We have an entirely new resource binding model that exposes the raw GPU hardware responsible for resource binding. We have multi-threading. You can, of course, now utilize multiple CPU cores to perform a variety of rendering operations on multiple cores, and we'll quickly talk about what those are. And then finally, resource allocation and how you store buffers on the GPU. We've provided a lot of new tools for the apps to take buffer allocation management and aliasing and lifetime into their own hands and do it more efficiently than the driver can. So with resource binding, hopefully you've had a chance so far to attend other DirectX 12 talks where we've given a more general API overview. This is a very complicated and complex area of the API. But for the purposes of this talk, we're going to touch on 2 areas that enable dramatic performance improvements, dramatic CPU efficiency improvements in your app. And the first is descriptor heap access, and the second is root signatures. So what is a descriptor heap? A descriptor heap in DirectX 12 is the actual GPU memory that controls how resources are bound to the GPU pipeline. In DirectX 11, you might call an API to set to bind 128 textures a particular pipeline stage. What the driver would do is it would allocate memory out of this heap, and then in a separate operation, when that time for that draw came, would set a pointer in a register somewhere to say, these are the textures for this draw call. Use this offset in this memory. So with DirectX 12, we've exposed the actual descriptor heap to the app itself, and you can allocate individual resources and individual bindings out of this heap. And as we'll talk about in the next slide, you can do it in a much more efficient way because you have higher level knowledge of how the app is going to be using resources. And the second area is a root signature. This is a API component we're very excited about. And the way to think about the root signature is it's basically, if a draw call is a function, it's a way of efficiently specifying the arguments to that function in a variety of different ways, depending on your app's use cases. So there are 3 ways with the root signature to pass bindings to a particular draw call. You can, like DirectX 11, call an offset within a descriptor heap. I want this group of textures, I want this group of UAVs for a particular draw call. But really cool, really powerfully, you can also put the texture bindings in the root signature itself and avoid that indirection into the descriptor heap. So if you have a very high frequency, very commonly used buffer, you can put that within the root signature itself. And GPUs can actually avoid an indirection and be much more efficient than what was possible under DirectX 11. And finally, you can just put arbitrary constant data in the root signature itself, and again, avoid any sort of indirection into to the GPU. And this is more efficient for the GPU. GPU hardware can take advantage of this information you're providing it to use registers, to use various other hardware to perform these bindings in the most efficient way possible. But it's also just a lot more convenient for your app. The driver will handle, for high-frequency updates, you don't have to worry about managing the lifetime of these different buffers. You can set it for a particular draw, and then the next draw, you can use that same place in the root signature to place another binding. So it's very efficient and very easy to use. So there's a few best practices. How do you actually use these constructs to get more performance? How do you do things in a way that exceeds DirectX 11? So for descriptor heaps, the real value that descriptor heaps provide, one of the primary values, is you can create your descriptor heap up front. You can populate it with the CPU, with a memory that describes what a texture is, where the texture is. You can do it up front at level load time, and you can group these together. And then the other half of binding, setting a register somewhere, is something that you do during the game time. And changing that register is extremely efficient. And by splitting these up, you do the expensive work up front, and then during binding time, you're only changing a single pointer somewhere in the GPU. So you can get great efficiency improvements this way. Something to avoid, something to be aware of has cost, is changing descriptor heaps. This is, if you want to have more than 1 million entries, on DirectX 12, all descriptor heaps support up to 1 million entries, at least 1 million entries. If you want to go beyond that, you can change between multiple descriptor heaps. And just something to be aware of is that there's a cost here. Whenever you change a descriptor heap, the GPU has to idle and wait for all existing work to complete. So we think that 1 million entries is good for most scenarios. The general way to think about this is maybe 1 descriptor heap per frame. And if you're double buffering your rendering work, you can maybe have 1 descriptor heap per each alternating frame. For root signature, there's a number of ways that you can basically help the GPU out. By keeping a root signature small, it has to alias less data across different draw calls. It can use what the resources available on the GPU, the fast paths you might think of to store the resources there. Take advantage of inline descriptors of data. As we said, this avoids indirection and can be more efficient. Avoid binding unnecessary shader stages, pipeline stages. In DirectX 11, you would bind a resource to a particular pipeline stage. In DirectX 12, you can bind a single resource to all pipeline stages. And this is actually really tremendous if you can effectively use this resource on all pipeline stages and reduce the number of total resources you have. But you can also, you want to make sure that you're not unnecessarily doing this, so you're only binding a resource to the stage that's necessary. So this is, just to reiterate, this is an area where you can move the needle on CPU performance. Take advantage of the new flexibility here. Multi-threading. In DirectX 11, the driver would create a background thread outside the app's control and silently move work from the app thread to the background thread for processing. In DirectX 12, multi-threading is, of course, app-controlled, and it's a first-class citizen via ID3D12 command list. There's no more immediate context with kind of helper-deferred context. Each command list is totally independent and equally efficient in generating rendering commands. So we've talked about multi-threading in the past. The point to reiterate here is that it's not just command list creation. In DirectX 12, all drivers support efficient PSO creation, supporting creating shaders on the GPU, but also creating resources and streaming in texture data. You can now do that across multiple threads. And finally, just something to call out, you might have a game or you might have a title that has a serial workload where you can't efficiently go wide just because you might not be able to predict what work items might come next. Our recommendation is to create your own background submission thread. You can do this a lot more efficiently than the driver could because you know what parameters you care about, you know what data you need to pass to the background thread, and you can control exactly when that work is being passed if you know that you're going to have a lull time on the app, for example. So that's multi-threading. DirectX 12 is built around multi-threading and enables you to be very efficient there. The third area is resource allocation. In DirectX 11, we had the concept of a map, write, discard operation. you would tell the driver, I don't care about the previous contents of a particular resource buffer. Just give me a new buffer, one that's not going to be in contention with the GPU and one that's not going to cause a GPU stall. In DirectX 12, we're giving you new tools like fences, telling how far the GPU is in execution, as well as the ability to create one large allocation and place multiple resources within that allocation to put apps in charge. And finally, these resources can be persistently mapped. You no longer have to map and unmap before you use these and consume these on the GPU. So the places that your app can take advantage of the higher level knowledge it has is to use an appropriate number of fences on the GPU. Your app can say, I only need to care about fences at the frame granularity. I don't need to be in a hurry to clean up resources because I know I have plenty in memory. So maybe you're only cleaning up once every frame, or maybe once even every 10 frames, depending on your app scenario. But you can also expire resources based on engine knowledge. One powerful technique is to take advantage of using your engine knowledge to determine when a resource is in use instead of actually explicitly synchronizing with the GPU. So this is a really cool area that can improve performance. So to talk about and to show off what this looks like in the app, I'd like to invite Dan Baker up to the stage to talk about what this looks like in Ashes of the Singularity. Thanks, Dan.
Wait, is it the big green button or the big red button?
Green is forward.
Okay. It's a green button and a red button. I didn't know what that did. Okay. All right. So we just announced our latest RTS, Ashes of the Singularity, and I'm going to talk about all the exciting things that are in DX12 that really buy us a lot of performance. When we designed Nitrous, this isn't entirely true. When we designed it, we didn't even have the next generation API, so we started looking at DirectX 11 and how to drive it efficiently. In our design paradigm, we came to this realization that textures are never accessed one at a time. We always, everywhere in our engine, package them in groups. And so we decided, well, let's take this one step further and really embrace this concept. And when we started talking to Microsoft about next generation APIs, we were really emphatic that it's very unlikely in almost any engine in a realistic situation that you're going to set a texture at a time. And in fact, it's fairly straightforward to package things up. A good example is if you have a model rendering on the scene, you might have a diffuse map, a specular map, some material masks, et cetera, vertex buffers, and there's no chance that you'll ever set one of these one at a time. They're always going to set together. So we built this into our engine concept very early. And internally in the engine, we called these texture sets. And it turned out that texture sets exactly mapped to a descriptors group. The other interesting thing is when we created these, when an asset was loaded. So if you do it right, if you embrace this concept early in your engine, which I highly encourage you to do, you can actually get to the point where you're never creating an actual descriptor during a frame. You're only creating them during your loading process. In fact, we got to the point completely naturally, it wasn't something that we set out we had to do, where we almost never create a descriptor set during an actual frame. The other thing that we immediately did is we always treated all the shaders as one monolithic block. We considered it, you're running a big program on the GPU. The fact that there's vertex shaders or pixel shaders and geometry shaders, that doesn't really matter from an application standpoint. We know we have a program that we're going to run. It's going to consume some data and produce some triangles out. And very early on in our process, we said that's the underlying primitive in the engine, and we've been completely happy with that. And finally, we had this observation that even though I don't know what the permutation matrix is, it's probably in the millions of all the different possible sampler state, what we noticed is we use approximately 6 of the combinations. And so internally in the engine, we decided to just build the small number of samplers that we actually ever ended up using. And we also noticed that we never really had a case where we'd ever change it dynamically. In fact, what we really noticed is that the sampler, or what sampler used, was always based on the shader's knowledge of it, not the texture's knowledge. So in fact, it was predetermined what sampler was going to be used. And so DX12 has the concept of static samplers, which is this observation that these samplers are not going to be changing and it's not interesting for us to change them. And there's a lot of advantages for doing that. Let me go to the next one. The explicit resource management is also a huge win. And in some sense, when you're building an RTS or a strategy game, the resource management is very different than when you're doing an FPS. And unfortunately, the memory managers are sort of general case memory managers, and we're not able to provide context to the GPU about what's going on, or the Windows memory manager on previous versions of Windows. A good example is that we have groups of lots of units in the screen, and each unit might have a different texture associated with it, which might have a different allocation backing. But if the way the tracking worked on DirectX 11, we had no control of what was resident in the GPU and what wasn't. The memory manager just tried to figure this out. And one of the things that could happen is if you're on one part of the screen, all of a sudden there was not a reference to a specific unit because it didn't happen to be on that screen. If you suddenly switched to another part of the screen, it would sometimes cause us huge stall because the memory manager decided to, oh, it wasn't resident, now I need to page it in, and then he flipped to another part of the screen and it decided to move memory around again for no reason. So having explicit memory management allows us to pin resources. It's actually not that complicated in a strategy game. You might have to access the memory at any time, so you need to keep everything resident. But we actually couldn't do even such a simple case on previous generation APIs without doing some rather dirty things that we didn't like doing. There's really, once you also group resources into these bigger groups, resource management tracking becomes way simpler. Doing an individual track on an individual texture, when you have 10,000 batches and thousands of textures, becomes a lot of bookkeeping that's utterly unnecessary because it's already established that there's these big groups of units that all reference the same sets. So we actually go one step further and we pull whole sets of assets that we know are all likely to be used together, and we just pay the cost or amortize the cost over a huge group of it. For example, if you had 7 tier 1 units that all have their individual textures, there might be a total of 50 textures and 30 vertex buffers or all of our index buffers, et cetera. There's actually no reason to manage the memory residency of that separately, which is what you had to do in DX11. Or what was sort of could happen under the covers. We could actually manage that entirely in one chunk, which removes massive amounts of overhead and increases the reliability. What we have found is generally we have 2 categories of resources. We actually allocate one giant pool for frame-specific things and manage the memory traffic through there more explicitly. And in our talk yesterday, I went into some of the details in that. And it turns out that this sort of 2-class thing, you have something that changes every frame and something that's basically static, is a very, very good approach. Now, oh, demo. Now I get to show you fun stuff. And the soak test, it's been running for half an hour and hasn't crashed. That's awesome. Okay, this is our game running. And as you can see, we have lots and lots and lots of stuff. We are handling, I mean, obviously the batch count is changing. If you see on the corner, right now it's not that high, it's only a couple thousand. But one of the things that's very important when you're building a strategy game is that we don't know what peak load's going to be. So people come to me all the time and say, Dan, you can do this, you can do that, you can do this, and you get more batches. Well, we could possibly, in an average case, get that, but the only thing we really care about is that worst case. And unlike an FPS or a racing game, we just don't know what the user's going to do, and we really don't want to limit them for what they're going to do. So you can see these battles can get quite intense. And let me zoom the camera out here. Yeah, in this game, we really wanted to let you have thousands upon thousands of units. We didn't want to limit the design and limit the zoom out. We didn't want to drop the icons or do any of some of the tricks. In this particular shot, we have about 25,000, but we have cases in this where, let's see if I can find one. There are cases in here where we'll spike up to, depending on what's going on and what weapons are fired, we can hit 40,000 batches. Now, I'll point a couple of numbers here. This is running on it doesn't actually, is it clipping? Yeah. Oh no, it doesn't. It clips on this, but not on that. It's awesome. This is actually running on an AMD 8350, and you can see that despite these massive, massive amounts of count, the total amount of time in driver is only about 6 milliseconds. And we have hundreds of thousands of particles, and all sorts of stuff going on. So this is fantastic. Okay. How do I switch back to the PPG? All right, I'm going to switch back to you.
Thanks, Dan. So very quick conclusion. There's many opportunities I hope you've seen today in DirectX 12 to take advantage of the new APIs to improve performance in your game. So the call to action is get started today. We have an SDK available. We have drivers available on AMD, Intel, and NVIDIA. You can check out some talks we've given previously on Channel 9. And I think that's actually it. So I think we have time for a Q&A. So if you have any questions, please approach the microphone up front so that the questions can be in the recording. Thank you. All right. Going once. Cool. I really encourage you to look at previous talks on Channel 9. There's a lot of information there. And the link here has a lot of information on the SDK and best practices there. So thank you very much.